So this was theoretically predicted since a long time, but experimentally never realized. And there was a lot of debate whether this would really work or not. But finally, we experimentally managed to achieve this 18 years after the discovery of graphene.
The most amazing thing that we observed is that we change the band gap of the barrier graphene, then we change the barrier curvature gradually, and we see the evolution of the valley Hall conductivity. So we use circularly polarized light to generate the photocurrent, basically. And this photocurrent only exists in one valley. And then when this photocurrent is moving, the trajectory is bent by this extra, or by this barrier curvature, by this field, and then we can see the Hall voltage.
So this is graphene, which is a lattice of carbon atoms, and it's only one atom thick. What you can do is find two layers of graphene that are stacked on top of each other, and it will look like this. This is called bilayer graphene. And bilayer graphene exhibits a very strong barrier curvature. What does this mean? Now let's have a look. So we all know that when you have an electric field, electrons will move in this electric field. When we add a magnetic field, we also know that electrons will start to bend. But what is special here in this bilayer graphene is that we created this effect without magnetic field, and that we did actually with light. So the light creates the electrons. So we shine circular polarized light. It creates electrons everywhere in this material. But these electrons feel this barrier curvature, and they start bending to the right. When we shine light with the other polarization, we create a different kind of electrons that are bending to the left. It's only the type of polarization that determines the direction of the bending, and the more polarized light you shine, the more they bend.
2D materials are highly tunable. It's very easy to tune it. Why? Because their surface states are fully exposed. And so you can put down gates on top of it, you can change its chemical potential, you can change its Fermi energy, but actually in the material that we were looking at, this thing called gapped bilayer graphene, the entire band structure of the material can be morphed by external gates. So so you might think that typically if I try to do this for a 3D material, it's going to be very difficult to actually do it, whereas in a 2D material you can actually do this.
Our device consists of I think 10 layers of two-dimensional layer. So in order to make it work, we will have to make a top gate and bottom gate and barrier graphene, and also the lead to extract the current. In this case, we have to use the stacking technique for firstly one BN layer, top gate, and another BN layer, etc.
It hasn't been optimized yet. It's still kind of in the stage where we're just understanding the physics of it. But you can think of this as trying to lay down a toolbox that arises from the quantum geometry of materials to be able to construct new types of photodetectors. But the idea is to add significantly to this toolbox, to find new ways of, new knobs of changing photonic properties. Maybe we might find new ways of photodetection, new ways of achieving, some kind of, plasmonic devices, non-reciprocal devices, and so on.
This can be useful for infrared and terahertz sensing because it is a semiconductor material with a very small band gap. So it can detect photons of very small energy. And that is useful, for example, for actually imaging in space. It's useful for medical imaging, for example, for tissue, skin cancer. It is also useful for the security applications for terahertz, for example, at airports, for inspection of materials. You can think of a production line of cars where you want to rapidly inspect the quality of the materials or the paint. So the next step is already ongoing, which is to further develop this technology, also to further understand the science, to see how can we make this effect even bigger. And with testing the sensitivity of these sensors and then try to see what application areas exactly can be developed.